Welcome back. All of the sorts that we've seen so far are grouped together in a group called comparison sorting algorithms. All that means is that whether we're talking about bubble sort or something more advanced like quick sort, at the end of the day, beneath the surface, the base comparison that we're doing is between two items at any given point. So we have one item on the left, let's say, and another on the right, and we're deciding which one comes first or which one comes second, depending on how we're sorting. So comparison sort just means we're comparing two things. That's the most we ever compare at a given time. We're doing less than versus greater than, and then we're deciding where that one item goes. So when we talk about average time complexity for something like bubble sort, it's O of n squared, same for insertion and selection sort. Then we saw a slight more than a slight improvement. We saw a pretty big improvement with quick sort and merge sort, which had average time complexity of O of n log n. So the question is, are there faster sorting algorithms? Can we improve upon O of n log n? Can we do better? And the answer is sort of. The answer is yes, we can, but not by making comparisons. So mathematically, there is a lower bound, an asymptote, for our average time complexity in a comparison sort. So no matter what the actual comparison algorithm is, what the sorting algorithm is, quick sort, heap sort, shell sort, any of the ones we've seen, cocktail shaker sort, haven't heard of that one. All of these, well, not all of them, some of them are slower, like we saw with bubble sort, but the best average case time complexity that we can ever hope for in any comparison sort is n log n. If you want to learn more about the reason for it, you can read this Wikipedia article. It goes into a little bit of a proof down here that explains how we arrive there. It all has to do with the limited information that we can gain from a single comparison. There is a mathematical bound to that. Anyway, that's not really the focus here because we have a solution. We have a way around this, but only in certain cases. So there are other types of sorting algorithms that are not comparison algorithms. And these algorithms take advantage of special properties of the data. For example, there's a group of sorts called integer sorting algorithms, and they only work with integers, with numbers. And we don't actually make direct comparisons. So one of those is Radix sort. So when I say that we don't make direct comparisons, I mean we're never actually comparing, is this number less than this number? Is this number greater than this number? So we end up sorting the data in a different way. So Radix sort is kind of fun, and it's very different than anything we've done so far because we're not making comparisons. So let's talk about how it works. So I mentioned it's a special sorting algorithm that doesn't make comparisons, and it works on numbers. So usually when this is actually used, it's used with binary numbers. Any number can be expressed in binary. Also, you could take any strings or images if you wanted to and convert them to binary. So it's possible to sort other data, but the actual data we work with at the time that we're sorting it needs to be numbers. And we're going to work with base 10 numbers like 950 or 17. So it never makes comparisons between two elements. It never asks what's smaller, what's larger. Instead, it exploits the fact that information about the size of a number is encoded in the number of digits. What I mean by that is that if a number has more digits, let's say a 4-digit number, it's larger than any 2-digit number. It doesn't matter what the two numbers are. We're not comparing the two numbers, but we know that something with more digits is larger than something with fewer digits. So here's actually how it works. We actually take a list of numbers. Let's say this is what we're trying to sort. We have some numbers that are 1 digit. These are all base 10, 2 digits, 3 digits, 4 digits. And we create 10 different buckets. And these buckets represent all of the possible numbers, the 1-digit numbers in base 10. So 0 through 9. So for every spot in a number, it could be a 0, a 1, a 2, all the way up to a 9. And what we do is we go through the entire list of our numbers, and we start by looking at this digit. So the first digit in the number from the right side. So 6, 4, 6, 3, 8. Okay? And we group them into buckets based off of that number. So you'll see all numbers that have a 2 in the rightmost position go in the 2 bucket. All numbers with a 6 in the rightmost position, whether they're 2 digits, 100 digits, it's just that we're looking at the rightmost digit. We group them together here. So we're not sorting them within this bucket. You can see that these are not in order. We take all 7s, all 8s, all 9s, and then we form them back into a list keeping the order that they're in right here. So this will be at the beginning, and then this number, and then this number. You can see here. So the numbers that had 2 as their last digit come before the numbers that had 3 as their last digit. And then at the end, we have the numbers with 9 as their last digit. Now we repeat the process, except we look at the next digit to the left. So we're going to look at this digit, and this one, and this one. Okay? So now we group them based off of that second digit from the right. So if we look at this column, this bucket, we're talking about 0, which this has a 0, 408 has a 0 in that position, 902 does. But then these numbers, which are 1-digit numbers, don't have any digit in that position, so we just put them in the 0 bucket. There's a 0 there, right? We could write any number as 07 is the same as 7. 04 is just the same as 4. So then we end up with, if we go over here, we've got all the numbers that have 5 in that position, all the numbers that have 8 in that position, and we're getting closer each pass through here. We're never comparing the numbers to one another. And now we reform them into this list, and you can see it's getting closer to being sorted, but we're still not there. So we repeat it again, where we're talking about the third digit. So the first, the second, the third digit. Do it again. Okay, so you can see the smaller numbers are already grouping up here. Then we have, for example, here, 5. This number has 5 in its third spot, and so on. And then we reform it into a list again, and then we have to go one more time. So the number of times we have to actually do this process depends on the largest number, how many digits it has. So we have a couple of 4-digit numbers, so we have to split them up 4 times. If we had a 10-digit number in here, we would have to do it 10 times. Okay, so here's our last time. So now they've been split up. We're talking about the 4th digit. None of these have a 4th digit. This one does, and so on. And then we form them again into our list, and we're done. So when I say we form them into the list, I mean we just take the order that's already in these buckets. So we start here, then here, all the way up to 902, and then we take this bucket. This one is empty, so this one, and we keep going. And now the numbers are sorted. So we never made any comparisons between the numbers in our list. Instead, we took advantage of a special property of numbers. So lastly, here's a nice animation of Radix sort. I'll hit play. What we do is we take a look at that rightmost digit and we group them in those 10 buckets. So if we're talking about base 7 numbers instead, we would have 7 buckets. But we're talking about base 10, so we have 10 buckets. Okay, and now we reform them. You can see the order we're talking about. We just pull them out of the buckets in the same order that they're already stored in. And now we take a look at the second digit from the right, and we form them into buckets. Okay? And again, in this case, our largest number is a 4-digit number, so we're going to have to do this process 4 times. So that was 2 times down. Now we have 2 more. So now we take a look at the third number from the right. And numbers that don't have a number in that position, we put them in the 0 bucket. And we're almost there. We just have to take a look at the 4th digit from the right and group things into the correct bucket based off of that digit. So we're almost there. So a couple things to keep in mind. In order to make this work, we have to be able to figure out a digit in a number at a given position. So in the next video, I'm going to talk about some helper functions we need to write. For example, I need to be able to ask, hey, what is the second digit of this number? What's the 4th digit or the 1st digit? And most languages don't give you an easy way of doing that. We have to write our own method to do it. So that's what we're going to start with before we get to the buckets. Anyway, that's Radix sort. It is a special case of a sorting algorithm that is not a comparison sort. It's an integer sort that works because of a special, I won't say loophole, but a special property. And it allows us to sort numbers very fast compared to having to do comparisons. Anyway, we'll implement it in the next couple of videos.